So again, as we did with the plate, flow between plates, for flow in a pipe, we're going to try to relate the pressure gradient to the average velocity, because that, as I said, is often what you know, because you might know a volumetric flow rate. If you want to know a volumetric flow rate or a mass flow rate of a pipe, all you need to do is capture the water in a bucket for a minute and then weigh it. So it's an easy thing to figure out, and then you could find that would give you your average velocity. So we'd like to know the average velocity as it relates to the specific velocity as a function of r, and also as related to the pressure gradient. So this is our definition of average velocity in a cylindrical coordinate system. We discussed this earlier as well. You have vz, which is a function of r, but then in order to integrate from 0 to r naught, you have to multiply by 2 pi r, because that's the distance around each circle as you go out into larger and larger radii. You have larger and larger amounts of fluid that have that distance, that speed, and then of course times dr, and then you divide the whole thing by the area of the pipe, the cross-sectional area of the pipe, which is pi r naught squared. So that's our definition of the average. So we're going to go ahead and take this integral, 1 over pi r naught squared over here, moving that into a denominator, and then 0 to r naught of our expression, 2 pi r times vz of r. So that's g over 4 mu times r squared minus r naught squared, and that's all just dr. So that's my integral, 2 pi r times g over 4 mu and times r squared minus r naught squared. And then that's actually not a hard integral to take, happily, once again. So I can pull the g out, because that's constant, and I have 2 mu over r naught squared. All those things are constant, so they all come out of the integral. Notice the pi's cancel here. That pi is going to cancel this pi. Of course, the 2 and the 4 divide. That's why you're going to get the 2 there and the 4 here. So they're going to cancel, end up with just a 2. So anyway, we'll start with this 0 r naught. And then the r is going to multiply in here, so I'm going to have r cubed minus r naught squared r dr. So there's my simplified integral. This is still a 4, but it's going to become a 2 in a second. So then here I got no 2 in the numerator, and I got 2 mu r naught squared. And then I'm going to take this integral, so that's going to be r to the 4th over 4 minus r naught squared times r squared over 2. And that's all evaluated at 0 and r naught. So that's pretty easy. G over 2 mu r naught squared. Of course, r naught going in here, I get r naught to the 4th over 4. And I get r naught squared times r naught squared is r naught to the 4th over 2. So it's 1/4 minus 1/2 there. The average velocity is equal to negative 1/4 of this. So it's g over 2 mu r naught squared times r naught to the 4th over 4. And of course, I will clean that up for my final form here. U bar is equal to minus g over 8 mu, and then the r naught squared, of course, is going to kill 2 of the r naught to the 4th, so that's going to be r naught squared up in the numerator. Make sure I didn't make any mistakes. Looks good. So that's my expression that relates average velocity to the pressure gradient. And it's, again, expected if the pressure gradient is negative, then we have a positive velocity. Pressure gradient negative means dp dz would be, pressure would be decreasing from the inlet to the outlet of the pipe. So that's going to be a positive velocity. Of course, if I have a positive pressure gradient, so this pressure is higher, it's going to pump liquid back the other way. Of course, viscosity is going to slow the flow down. Having a bigger pipe is going to make it faster. So that all makes good sense. Finally, we're going to look at the VZ max. So VZ max, where is the fastest flow? Well, the fastest flow, we know it's a parabolic profile. So we know that the fastest flow in a parabola of that kind is going to be at r equals 0. So we know the profile looks something like this, with the fastest point being right there in the middle. So that's what we'll try to evaluate here. So that's going to be g over 4 mu times, our expression was r squared minus r naught squared. So r squared minus r naught squared evaluated at r equals 0. So I put in 0 for r squared. So I get that Vmax in the z, Vmax z, is equal to g over 4 mu times negative r naught squared. I didn't write that very well. I'll write it so you can see it better. Vz max is equal to minus g r naught squared over 4 mu. So that's our maximum. Notice you can compare that to this, and you can see very clearly that Vz max, Vmax, is equal to 2 times the average. So whatever your average velocity is, your maximum velocity is exactly 2 times that. And it's 2 times this gives you this. So that's how you end up with, that's how you can calculate your maximum velocity. Pretty simple. If you know the average velocity, your maximum velocity in a fully developed pipe flow is just going to be 2 times that average. I'll word it there so you can see it better. Okay.